All right, hello everyone. I'm Dave Leone. I am the technical marketing engineer for a software product we have called Intel Cache Acceleration Software. I'm going to talk to you a little bit about the features of the product and then a particular software-defined storage use case where we found that we could add a lot of value and how that went. Okay, so the use case that we're talking about with software-defined storage basically is when you have a lot of small files that you need to deploy across your SDS. So whether it's Ceph or Swift, whatever you have, you'll see a little bit more about the particular files that I'm talking about. But if you have a lot of small files distributed randomly across your storage, for hard drive-based solutions, small files create large problems. So for spinning drives. So this is going to result in high latency, low throughput, and high amount of over-provisioning needed in order to meet the throughput that you want to deliver to your customers. So the specific use cases, we've been working with Yahoo with their products, as Jay mentioned, Yahoo Mail, Flickr, Tumblr, those kind of products. They wanted to experiment with software-defined storage, particularly Ceph. So Intel, over the last year, between Intel Labs, which is our research arm, and NSG, which is the group I'm in that owns the cache acceleration software, we invented a new approach in order to improve their Ceph cluster performance, resulting in 2x throughput and half the latency for their files. And I'm going to go into detail on that. So the solution is an Intel NVMe SSD paired with the Intel CAS software, version 3.0. I'm going to focus on the Linux software. That's what we used for this solution, but we have both Linux and Windows version of the CAS software. That software implements unique software optimizations and tunable and selective hint-based caching approach. As opposed to traditional LRU-based eviction, we now have hint-based caching and priorities. I'll talk more about that too. So that allows you to increase your storage cluster performance and save cost at the same time. All right, so this is to cover some of the features of the software. The latest thing is this new I/O classification capability. So the ability to selectively cache I/O by size and type and give it a priority. That'll let you improve your overall I/O efficiency. Spinning disks are going to still spin to capture the sequential reads, but as you'll see, the primary improvement in performance comes from caching the metadata in this case. And then our software has both read and write caching capability. So we have 3 different caching modes. We have write through, we have write back, and we have write around mode, which is sort of an optimized write through. We have the ability to do multi-level caching. So the idea is that you could cache your hard drive data to an NVMe SSD in write back mode, and then you could create a RAM disk and cache in write through mode to the RAM disk your hottest data. And in the future, obviously, replace RAM disk with Optane and cache in write back mode at that level as well.
Is this still a file system filter, or did you move it down to the block level?
I will get there. It's block level. Yeah, so that's we got a slide that's very detailed coming up on the solution.
I can wait. Okay.
And then the Intel CAS Linux software license is included with Intel NVMe SSDs. We have bundle pricing, so we have a bundle where you purchase the SSD, you get a license for the software as well. All right, and then this is just explaining for write back mode. If you're not familiar with how caching works, which I suspect a lot of you are, but basically when you do a read, you read the data from the back-end storage and write it into the SSD at the same time you return it to the client. When you do a write, all the writes are returned at SSD speeds. So in write back, you write to the SSD and then you return to the host. And then any subsequent reads of anything you've read or written come at SSD speeds as you've put it in the cache. And then in write back, dirty data is written opportunistically to the back-end storage. All right, so now talking about the solution. Something called differentiated storage services. This came out of Intel Labs, which I said is our research arm, so their storage-driven research and innovation group. It was initially deployed in Lustre Enterprise Edition. So the capability is there in Lustre Enterprise Edition. They didn't have a caching solution to take advantage of these hints that were being passed down through the file system. And they have a roadmap of future technology-driven enhancements. So they have new capabilities that they're working on experimentally at this point. For those of you that are familiar with networking, this is very similar to diffserv in networking, which was IP packet classification for quality of service. This is a storage quality of service capability.
Can I ask a Brent? I don't know.
Sure.
So, we just got the crap scoured out of us for whatever. And I was wondering about, and it's just a random thought, does caching, does that increase the number of times the data is moved around as I'm writing it, and therefore increase the number of times it could be silently corrupted?
Yeah, I don't know. I don't know the answer.
Great, awesome question.
Maybe Vinod could,
Well, you're writing more
talk
data.
about that.
Okay, points for saying I don't know, and
Yeah.
not talking for 4 minutes without saying anything.
All right.
Yes.
Thanks.
Big props.
Yes, it would do that. So unless you
Mike.
Oh, you don't have a mic on.
Yeah.
Would Vinod, yes. Here's a mic coming over here. Yeah, yes, caching would increase the amount of times the data is moved around. Cache gets moved in and out of data gets
Right.
moved in and out of caches, gets evicted. Sometimes it's read, sometimes it's not. It's definitely increasing the movement. The question is, when would the bit flip happen? And to your earlier point, on the read or on the write. But yeah, it increases the opportunity.
Data gets moved a lot as it is. Yeah.
Right. I'm just. Yeah, it was just a thought, I mean, like I said, you scared the crap out of us for a while. I was like, wait, this would move the data around more, and okay.
I don't think it's recompiled on a cosmic grid, though, right?
Right.
and if you have even the lowest level of protection,
like
parity, even if you have the lowest level of protection on the cache, like parity, the host can take action on that as long as there's some notification that there's something went wrong. Then at least it won't be silent.
Okay.
Yeah, then you detect it, and you have to hope there's someplace else to read it from.
Okay. So the productization of this differentiated storage service technology comes in Intel CAS. The feature is called I/O classification. And what it allows you to do is, this is broadly applicable to Linux-based software-defined storage systems. This is on our Linux software. It can work pretty much for any software-defined storage system. Our software works at the block layer. I'll get to that on the next slide. It allows you to classify I/O requests in the software, assign policies to those I/O classes, whether I want to cache that particular type of I/O or not, assign priorities and enforce those priorities in the storage system. So for eviction, rather than a typical LRU-based eviction, you can assign priorities to different types of I/O and say, I want to give this the highest priority to keep it in the cache and evict lower priority things first.
What are the filter parameters? I/O size and what?
I have a slide on the classes too, so we'll get to that on the next slide too. All right. Here are the classes, to your point. So the classification schema you see over on the right-hand side, basically, these are the classes that we identified.
X.
So we have all metadata in one bucket, and then we're able to identify if it is a file I/O, what the size of that I/O is going to be, and classify each of those individually. So if you know your workload, you can say, hey, I really care most about metadata and 4 meg files, so I'm going to make those two my highest priority, make everything else a lower priority, or maybe even not cache anything else. Just cache metadata and 4 meg IOs. Right? As I said, Intel CAS operates below the software stack at the local file system block layer. So what that means is you don't need any software modification to your software-defined storage system in order to use this capability. You just drop this in with an Intel NVMe SSD and you get better performance. That's the way it works. And as I said, ability to selectively cache and evict based on the block type and priority. So you can turn caching on or off for each one of those IO classes. You can give each one a priority. Right? What this does is it enables a new approach of using a very small cache to get the best price to performance trade-off. So in Yahoo's use case, we ended up caching just the metadata, not the files, and you'll see why. So you can use a very, very small cache to get the same benefit that you would using a larger cache with typical LRU-based eviction.
Being able to selectively cache the metadata is cool as a bow tie.
Cool. I should have worn a bow tie, then I'd be double.
You want to borrow mine?
Okay. No, we're fine.
I have a sequined one with LEDs.
All right.
I look stunning in sequins.
Okay. So let's talk about the actual Yahoo case here. So like I said, Yahoo Mail, Flickr, and Tumblr, all of that data is small files. So you got mail attachments, you've got photos, and you got small videos, right? Then add on top of that the fact that Yahoo's interest is in getting maximum utilization out of their storage space. So rather than doing replication, they were interested in doing erasure coding. So they did A+3 erasure coding, which takes those already small files and breaks them up into 11 smaller pieces. So for example, 1 meg file becomes 11 smaller files of 128K each. What you end up with then, on every one of your OSDs, your storage disks, you end up with hundreds of millions of these tiny files. Reconstructing one of these objects, so one file, requires you to gather at least 8 of those 11 pieces before you can put it back together. And then getting each one of those slices, because you have hundreds of millions of small files on your file system, requires you to walk through 4 to 6 inodes on the disk in order to get to that slice. So walking through the metadata takes a long time and increases your latency to object reconstruction. Right?
Oh, okay.
And just curious, were they doing, was this geographically segregated erasure coding, or was this all within a data center?
It's all within one data set.
Okay, all right.
But even so, it's across OSD nodes to
Right,
reconstruct
right.
this object, right? So you had to wait for each one of those 8 pieces to be gathered from all of those nodes in order to put the object back together. All right, so overall object reconstruction latency is dependent on the worst latency of any one of those slices. So that tail latency problem. So if I'm going to read from the hard drive, I have to read 6 inodes plus this data slice. If those get poor latency, if any one of those slices has poor latency, you have to wait for that one before you can reconstruct the object.
Well, you'd need 4 to have bad latency, right? Because you just need 8 out of the 11, so you'd need 4 of the 11.
That's true.
Right. The
So-
latency of the 8th to respond.
Yeah, the latency
is
of the
effective
worst
latency.
one of the 8.
Yeah,
8.
of the 8 that do respond. Yeah.
That's right. Yeah. Okay, so solution to this problem is Intel CAS plus NVMe SSDs. So Intel NVMe SSDs deliver consistent performance, consistent latencies. So the idea is cache the file system metadata to eliminate the inefficient disk accesses for the inode reads. We still read the file data from the disk as it's a sequential, pretty fast read. We really reduce the chance of having poor tail latency. So if you look at this on the right-hand side, the gray is the hard drive latency curve and what your worst case tail latency could be when gathering these pieces off of the hard drives. And then with CAS, putting all the inodes on the NVMe SSD basically shifts that whole curve left because NVMe SSD latencies are way better than hard drive latencies to begin with. And it tightens that curve because of the consistent latency performance of the NVMe SSD. Okay, so technology benefits, like I said, delivers data at consistent SSD latencies, reduces the worst case tail latency, reduced latency variability improves deployment and support predictability, and then increases our throughput with average lower read-write latencies and reduces your over-provisioning requirements. So this is one major benefit is if you can increase your throughput 2x, the amount of servers that you need to deploy to deliver that throughput to your customers is cut in half, right? So if you could speed up your cluster and at the same time save money, it would be a no-brainer, right?
Faster and cheaper.
There
What's
you go.
wrong with that?
All right, so after we did all of that and put all of that in place, what we ended up doing was for each OSD node, object storage node, we put in an Intel NVMe SSD. We used 1.6 terabytes of SSD space for 80 terabytes of hard drive backing store space. So a very small cache. We actually used 100 gig of that space for journaling, for the Ceph journaling, and then 1.5 terabytes for caching, all right? And Yahoo performed this testing in their lab, and these performance numbers are public. So what they did was they tested at different numbers of requests per second, so at different throughput rates, what was the latency for reads and for writes. And they did that for different levels of cluster fullness. So as the cluster gets more full, seeking on the hard drives to find those inodes and to find those files introduces more latency. Putting all the inodes on the SSD, you don't have the seek latency, right? So if you look, they did testing at 30% full and 60% full using CAS versus using just the hard drive
Okay,
only.
that's the system 30%, not the cache 30%.
Right,
60%.
the cluster data is 30 and 60% full. Okay, so the backing store. So as you can see with this chart, as the hard drive only solution got more full, the latencies grow apart, right? Because you have to seek farther to find those inodes and to find those files.
Be curious, what would be if it were 80 or 90% full? Like, would it get even worse?
It would get worse.
Yeah.
Yeah. And typically you don't allow your cluster to get, you have a certain buffer, right, of over provisioning. So I think typically we stop at 70% and deploy another cluster, right? Yeah, so anyway, then if you look at the CAS solution, right, the lines are separated, but they're very close together. So all those inodes, this shows you the benefit of serving those inodes out of the SSD. Because I didn't have to seek to find those inodes. Whether I'm 30% full or 60% full, my latency is almost the same. The only difference is still seeking to find that file once you do the sequential read of that file, okay? And then if you look at any given number of requests per second, the performance of CAS, just caching those inodes versus the performance of the hard drive solution, you're at, 50% the latency, right? And then over on the right side, similar results with one other exception. If you look at the hard drive only solution, as you got to 1200 requests per second with the hard drive only solution, the system could not handle that number of requests per second. And this is an 8 OSD node cluster. And 1200 requests per second, Ceph has a timeout of 20 seconds for getting your request. Over 30% of these requests failed to return, and Ceph killed them with the hard drive only solution. Whether you were 30% full or 60% full.
So is that a request for a specific strip or?
For a particular object. So 1200,
okay, so
1200 1 meg object requests per second.
Right, it's above the EC.
Yeah. And then the objects that did return had an average latency of 2 seconds, which is really, really long. Now, if you look at CAS, also at 1200 requests per second, we returned all of the requests, and they were at 250 milliseconds, whether you're 30% full or 60% full.
250 versus 2 seconds?
Versus 2 seconds.
Nice.
Yeah. And we returned all of them versus failing 30% of them. So
There might be something to this flash thing.
Oh yeah. So so CAS plus Intel NVMe small cache basically allows you to get something out of Ceph that you could not otherwise get, which is this extra throughput in your cluster, and you get lower latencies, half the latency, and you don't have to over provision. So that's the key takeaway here.
What I'd be curious about, because your point is, CAS good, right? What I don't see here is, at least I don't think I'm seeing it, is what the flash would be without the CAS.
Okay, so ideally, if you wanted to get the absolute best performance, your entire cluster would be NVMe SSDs, right? Sometimes you can't afford to do that. And in a lot of cases, for your warm tier data, you don't want to spend the money to do that. This is really designed for the warm tier, not the ultra high hot tier, right? So in the warm tier, we can give you 2x the performance and save you money while doing it and using a single Intel SSD per storage node.
Yeah, but this
Does that make sense?
This is like a 1.5% size of storage cache. So the cost difference is enormous between.
That's true. Yeah, if you wanted to do 80 terabytes of NVMe SSD storage, a lot more expensive. But if you really, really need the performance, you want to go there. Yeah. Okay. Any questions? This is what I
And
got.
of course, it comes with the SSD.
Yeah, you buy the Intel NVMe SSD bundle, you get the software.
So I get the software if I pay extra for the drive. Just be clear.
Right, bits back. Could be a
Just be
cosmic rate.
clear. It doesn't come with it. It comes with it if I pay for it.
No, you buy an Intel NVMe SSD. The license to software comes for free.
Comes with it.
Okay, the way it was described before, it sounded like it was being offered as a separate
It's a
bundle.
bundle, which means
We need to do both. The thing is, if there's a
Yeah, it's a bundle. You can buy CAS separately, or you can buy it in the bundle with an SSD. And when you buy it in the bundle with the SSD, it essentially is free.
The SSD
comes
is the
with
same
license.
price.
Don't buy somebody
In the
else's.
bundle, not in the bundle, the SSD is the same price.
And if I buy the CAS separately, I can't use it on anybody else's drives.
No, you can use it on other.
You can. So
Okay.
the pricing, the licensing is priced favorably with Intel SSDs with the bundle. Actually, Ron can describe more about that if you want.
Yeah, I think it. Does that work? So,
Yeah, there's no PA.
not enough coffee today. So we sell a standalone license, and then also what we have is the single part number that includes the software license that is priced the same, and it's only on Intel NVMe SSDs.
No, I'm just thinking as a reseller, as I'm getting ready to talk to customers, I just need to have an understanding of
Right.
how to describe the product. So I got a better idea now. Thank you.
So yeah, I can buy it separately. So what is it when I install it? Does it go in as a kernel module? Is it?
Yes,
How's it work?
the CAS software is a loadable kernel module paired with a user space admin tool.
Okay. And are there limitations about file systems that it will work on? Could I?
It's been validated with ext3, ext4, and XFS on the Linux side.
And I've just moved to Btrfs, so rats.
Yeah, now we're not saying that it won't work. We're just saying this is what we've validated with.
Yep.
So,
Okay.
You are talking about an admin tool, but actually we are talking about Ceph, potentially Yahoo with thousands of nodes, REST APIs, whatever, to manage all this nodes, cache, whatever, or
yes, so that's true. So what was the question? Sorry.
the question is, do you have APIs to manage everything from a single command? I want to modify the block size for the caching on 10,000 nodes. I want to
So we
write a command.
Right, gotcha. That is definitely scriptable. We don't have a specific application to do that, but you can script that pretty easily. We do have a batch remote installation capability for CAS, and we're constantly looking at those type of things. So all of our development is use case driven. So anytime we see a need, we implement those things.